Welcome back, everybody. This is now the Frontiers part of the symposium. We'll have three speakers. I'd like to introduce our first speaker, Ian Foster from Argonne National Laboratories and the University of Chicago. Please welcome Dr. Foster.
Thank you. Good afternoon. It's a great pleasure to be here. It's been a fascinating couple of days so far. So I'm going to talk about, well, a few different things, but partly what I want to do is to motivate and introduce work we're doing at Argonne, designing and building a foundation model called Aurora GPT, and hopefully we're going to identify ways that we can work together on that. So a little bit, first of all, about context, why people have expressed all sorts of reasons for why they're interested in this foundation model technology. For me, and I think many of my colleagues, it's about observing and hoping to drive continued evolution in how we undertake scientific research and discovery. I won't go through the elements on this slide, but point out that we're getting, we believe, to a point where rather than applying theory, computational methods, data-driven methods in isolation, we can apply them in a integrated manner such that we can accelerate the whole cycle of discovery by combining certainly AI, but in close conjunction with HPC and robotics, and I'll say a little bit about robotics later on, in what we might call an accelerated scientific method, in which, of course, humans are deeply involved, but the traditional, very slow process by which hypotheses are identified, ideas are, for testing hypotheses are developed, experiments are performed, data is analyzed, etc. Each of these steps we want to be able to accelerate, and it's very important that we accelerate all of them because as good computer scientists, some of us are computer scientists, we know that if you only accelerate 9/10 out of your steps in some process, you're still going to go very slowly because the non-accelerated step will be the rate limiting one. So there are many elements in this acceleration process, but if we look at the sort of fine print in each of these areas, we can see AI methods end up being fundamental in many of them. And I won't again go through details here, but just highlight some of the words, extracting and integrating large-scale knowledge, generating new hypotheses as we might undertake with generative models, automated discovery within robotic labs, collecting the data, and collecting not just data but knowledge, and integrating knowledge into knowledge graphs that can be reasoned over by machines, etc. So we need advanced AI methods to realize this broader vision. So what are those AI methods going to be? And of course we've got, 1956 was the term AI was coined, so we've got close to 70 years of research to look back on, but we do recognize that foundation models seem to be proving remarkably and surprisingly effective. And so, for reasons that we talked about a little bit earlier, are we really seeing evidence of homogenization and emergence? We can debate that, but clearly they are proving effective in ways that were unexpected, and we see no immediate evidence that they're going to stop becoming more effective, at least in the immediate future. So another hypothesis will be that foundation models are a promising step forward, a promising path forward as we pursue this goal of accelerating discovery. So let's look at the foundation models that we have available to us. Well, just pick one, for example. It's got a nice graph. This is PaLM, which is one of the larger models currently available. It's, as we well know, it's trained on large amounts of text from many different sources. But we might notice that science is a fairly small element. It is larger than adult, but smaller than sports in its knowledge. So we might therefore conclude as we think about how to apply foundation models to the problems I'm talking about, that we need models that know more about science, maybe a lot more about science. So how are we going to do that? Text, of course, is a wonderful source of information, and I probably won't spend much time talking about non-text data, but we do recognize that other modalities are important, but it has this wonderful property of having evolved as a means over many millennia, as a means by which humans explain themselves at least to other humans. So we certainly should be looking at as much text and code from science as we can get access to. I've listed here some of the sources that we might want to collect. So as many scientific articles as we can get, certainly. Various digital libraries. We have access to the wonderful OSTI library of all DOE scientific articles. It's not actually such a large collection, but it's probably useful. Archive, code repositories, etc. But humans can only type so fast, especially scientists. Non-scientists seem to be able to type at infinite speeds. Thus all the misinformation. So there's only still a relatively modest amount of text and code corpora, perhaps a few hundred million, equivalent of a few hundred million articles that might be available to us. So we also need to find ways to engage scientific and engineering data sets. And we'll come back in a minute to how we propose to go about that. So data is one area in which we need to focus if we're going to build a truly impressive foundation model for science. Another one, of course, is computing. So we've seen versions of this slide earlier, pointing out that, Palm here is at about 10 to the 25th floating point operations, was involved in training it. GPT-4 is estimated to be somewhat more than that. Other models being trained probably today are yet larger. Clearly, these are not numbers of computing, amounts of computing that we can easily harness. So it's a significant barrier to what we want to do. This 10 to the 26 will be 10 exaflops, or exaops, I guess, for 100 days. Substantial amount. So one thing we might conclude from that is that, as people have been saying, we need to build collaborations between universities and national labs. But the reason we need to do that is that we can't afford to build a lot of these foundation models for science. We can probably build more than one. We could build one on the Argonne computer, one on the Oak Ridge computer, one at NERSC, a few elsewhere, but we can't build dozens of them. So that's an important thing to think about as we move forward. So I'm from Argonne National Lab, and there we do have this Aurora supercomputer that we're just currently installing. So let me say a few words about that. So Aurora is a very big system, a lot of megawatts, a topic that I won't talk about, but it's an interesting thing to reflect on. 64,000 GPUs, Intel GPUs. It's projected, it's still being sort of finalized, the installation, but it's projected to be between 1 and 2 exaflops and probably up to 20 exaflops at 16-bit precision, which is what we probably can use for our model training. So here's a picture developed by my colleague Rick Stevens that, or I guess a spreadsheet, that talks about what you can do with a computer of that size. So if we're talking about a small model, like say Llama 2.7b, 7 billion parameters, our current state-of-the-art computer at Argonne, or the predecessor to Aurora, Polaris, with this can achieve, we can at least say a month on the full machine, we can train that model, which is certainly quite doable. In fact, we're doing it at the moment as part of the Aurora GPT effort. But trying to train a larger model, like say the trillion parameter scale that we're aiming for with Aurora GPT would be how many? 29,000 days. That doesn't seem very practical. So on the other hand, if we move up to Aurora scale with the 20 exaflop 16-bit precision that we have, we can talk about doing that in maybe 100 days, or depending on how many parameters we want. So it becomes feasible. It's a hero calculation. It's of the scale that has been done by these very large cloud vendors. It's not something we can do on a typical university or even NSF supercomputer center. We need something of the scale of these systems. So let's go say a bit more about what we're thinking of for Aurora GPT, and then we'll start talking about some of the issues we want to collaborate on. So there are, of course, many design decisions one could make in building a system of this sort, but we're thinking in terms of a general purpose, scientific, initially a large language model, trained on as much text as we can get, going to be fine-tuned for scientific assistant sort of use cases. We'd like to have the sort of entity that will be able to engage with a scientist as they go around that cycle that I showed you earlier. We're working with some international collaborators with the goal of making it multilingual, at least for Japanese, French, German, and perhaps some other languages. Eventually, not this year, but the next, we'll be starting to explore ways of making it multimodal as well, which of course we recognize is of vital importance. That's been discussed several times today and yesterday already. The strategy that we're adopting is one of building up a series of systems, starting with 7 billion parameter model, scaling up to ever larger ones, integrating more and more domain knowledge as we go, starting with text only, and then moving to multimodal models probably in the next year, which is not that far away. So let's talk a bit about the steps that we're following as we drill down to the training process. So we've seen versions of this slide already, I believe. This is from Andrej Karpathy's talk on ChatGPT. Training, so we probably are aware there's the pre-training process, unsupervised process, one where the model basically learns co-occurrence frequencies of words and relationships, a very data-intensive and compute-intensive process. There's a supervised fine-tuning process where you train on lots of demonstrations of what you would like to the model to be able to do, for example, act as a scientific assistant. And then we have these later steps that do some additional tuning around reward modeling and reinforcement learning. So each of these steps, in each of these areas, we can draw upon a huge body of experience from the community, but we also need to be thinking hard what is special about science and what do we need to do specially in that area. So we've organized ourselves in terms of the following teams, focusing in on the core here: preparing data, training the model, evaluating the trained model, post-training the model for instruct tuning and so forth, and this also requires evaluation, and eventually serving the model to, we imagine, thousands of people within the DOE system and in collaborating institutions. Serving is, of course, a very important element, and it's something where we need to be able to optimize a great deal to serve millions of requests on a day, is our expectation. And the data that we expect to be working with, 10 trillion tokens, say, of general text. We're working hard on that. And then a lot of domain-specific tokens, maybe another 10 to 20 trillion from areas like biology, chemistry, materials, astronomy. So we're very interested in talking to people about how and where to obtain those tokens, how to generate them, how to determine whether they're useful, and so forth. I'll just throw up this slide to show some of the people that are involved. These are so far primarily Argonne people, but we're starting to engage some external partners. For example, Bo Lee from the University of Chicago is working on the evaluation safety, the safety side in particular. But others, many of the others, I think you'll recognize. There's Arvind, who was speaking yesterday, and there are probably some others who well, none of them are here, but you've met them at various points. So let me just go through each of those areas quickly so that we can get some idea of what we're doing in each space. So data. Our goal is to get, say, 20 trillion tokens of high-quality scientific text, either human-generated text or in textual encodings of scientific data. And key issues here are: how do we do quality control? How do we document provenance? How do we do deduplication? How do we make it easy for people to generate subsets of different sizes? So I won't go into detail on what we're doing there, but those are the concerns that we have. I'll say a few words about data generation. So, there are maybe, let's say there are three sets of training data that we might want to use. We have general text and code, and there's close to an infinite amount of web scrape data that one can use, and that proves to be very useful in that people who have attempted to train science-related models on only scientific articles, they often find that they aren't very good at going, not surprisingly perhaps, going beyond the immediate domain of the articles that they're trained on. So it seems that many of the purposes we want to train on lots of web data, and that has many quality and deduplication or duplication problems. Then we have scientific articles, which hopefully the quality is generally better, not always, but there are a different set of concerns there. And then we have the potential, it seems promising potential for encoding scientific data, say data in relational databases or other structured sources in textual form. And this is, I think, Arvind or perhaps one of our students mentioned this yesterday. This is a template for encoding information from a genomic database called the SEED, and I've color-coded it a bit. You see there's a narrative, there's slots that need to be filled in with genome IDs and lengths and names. There's a bit of conditional text, is it a host or a disease, and do different things in each case. Run that through and you can quickly generate, this is actually not a disease, this is a chemical compound, but the same basic idea. You quickly engage and develop encodings of this form. So in this way, so far we're at the point of generating billions of tokens, which is a long way from trillions, but at least it's a step in the right direction. So that's a process that's continuing. We're very concerned about understanding how the encoding method and the encoding quality affects the capabilities of the resulting model. Training. I won't say too much about, happy to talk more about it, but the basic goal here is to be able to leverage the entire 64,000 GPUs of Aurora to train not perhaps the 7 billion parameter models, but ultimately the trillion parameter models. And we're in the midst of training, doing some reference tests here. We're training Llama 2, which of course is well known, but just verifying that it trains correctly on Polaris and Aurora, then training versions of it that have science data added so we can start doing comparative evaluations and also starting to look at scale-up issues. Now, evaluation is perhaps, apart from data, one of the most difficult and important areas to work on. So, as we all know, you can't improve what you don't measure. There's a whole industry of people out there building evaluation suites for large language models, which is great. We can leverage those. But there's only a limited number of people working on evaluation suites for science applications. So ultimately, people aren't going to be sitting down and using this model to do whatever people do with regular large language models, writing poems or writing memos for their offices. They're going to be asking deep scientific questions, or perhaps asking very mundane things like, what do you know about this particular peptide or bacteria, or how do you implement this particular experiment on a particular set of apparatus? And so unless we have evaluation suites that determine how well the model is doing at these things, we're not going to be able to improve the model and make it be better at those things. So the evaluation suites are a necessary but not necessarily sufficient step in that direction. So there's an excellent team led by Frank Capello, who's working on this. So, and he too knows how to use ChatGPT to generate images. Just remind us that the way that people do evaluation is they tend to be task-specific data sets that seek to evaluate the skills of models for a whole variety of different tasks. And some of those tasks are very well understood, and there are community standard evaluation suites. Others are less well understood, and there's many alternative options. And people may be looking to evaluate accuracy, success rates. They may be looking to evaluate things like safety, trustworthiness, and ethics. I won't go into details on those, but just point out there's a lot of general frameworks and metrics for doing these things. And so, just to pick one here, so GSM 8K, it's a set of middle school math word problems. And if you look at the rankings, you can see which model, how different models do on those middle school math word problems. And presumably we'd like Aurora GPT to do well on those problems, but it's certainly not in any way an adequate evaluation of whether it's useful for scientific purposes. For science, then, we have a whole set of additional things we want to evaluate. We want to be able to use these models at least to be able to extract, synthesize, retrieve knowledge based on the scientific literature and other data. We also presumably want them to be able to undertake reasoning tasks, for example, for purposes of hypothesis generation. We may want them to be creative, etc. There are presumably other things we want them to be able to do, which you may have thoughts on, or other people may have thoughts on. And there's a whole range of criteria that we're going to apply to the evaluation of these methods. So this group is hard at work on understanding these issues, and there are many things that are clear. We know we need to be able to, this is very mundane but important, we need to be able to run these evaluation suites at scale on our Polaris computer or on Aurora itself. But the thing is, what skills do we want to measure? How do you measure them? How do you select your questions, for example, in a question answering scenario to provide good coverage and also achieve depth? These are sort of open problems, I would say. And then also concern about contamination issues. So, if you ask a model a question that you might think requires some reasoning from the facts it knows, but it actually has seen an article that describes the exact answer to that question, that's not as useful perhaps as one in which you manage to train the model on a training set that doesn't include that article. So the contamination concerns are quite setting. So we're searching widely for evaluation suites and also building some of our own. We're working, for example, on building up databases of question answering pairs for science. So these are some of the applications, some of the suites that we're working with. I won't go into any detail, but just point out, we're at the point where we can now rerun these suites on our computers, which means we can, as we get new versions of Aurora GPT, alpha, beta, etc. We can test them quickly in a few hours. That's very important. We're collecting domain-specific benchmarks, and we're starting to develop our own, for example, something that we think could be a large community effort, although so far it's been somewhat hard to persuade people to contribute to this because it seems a bit dull, but it's important, is multi-choice questions. Questions in which that you can describe by a nice template. A question, some distractors, a correct answer, the difficulty. For example, this one. How many carbon atoms does 3,3-dimethyl heptane have? The correct answer is 9. It's got some associated metadata. It has some distractors. And that's a question that you can pose to any large language model and see how well they do. What? 3 minutes to go? Okay, well, I'm really, I thought I was on this. So, yeah, I'm not. So anyway, so this is going very well, although it's early days. What I wanted to say, that's one thing we've got to build Aurora GPT. Then we are very concerned about building out, working out how this model will act in a larger context, in such as here, and that we believe will require building out communities of experts that engage Aurora GPT linked with other, for example, foundation models trained in, for example, on materials data or chemistry data or biological data, and methods for engaging these different elements in ways that permit them, presumably the power of the whole of the ensemble to be more than the power of each individual. We're also very interested in engaging these systems in interacting with the physical world. So we're developing at Argonne a network of autonomous research labs that have various equipment that can be controlled by robotics. Lavin mentioned one of these yesterday. We're also thinking, and this is something I hope we can all be thinking about, what's the research infrastructure that we need to build if we're going to have these models able to interact with the world. Say one last thing. We certainly realize that we can't build this infrastructure together. Alone. So we've established something called the Trillion Parameter Consortium. Michigan is a member. The goal is to build an open community of people not all working on a single model, but sharing experiences and ideally avoiding redundant effort because there's so much to be done. And we've got quite a good number of participants already. If you want to learn more about it, you can take a picture of that, but hopefully the slides will be shared. And here's the summary of the things that I proposed we should be thinking about. I hope we can pursue some of these issues together.
Thank you very much for the talk. We have 5 minutes for questions.
Yeah, thank you for the great presentation. So my question is, when you train the Aurora GPT, do you anticipate it will follow the GPT path that first trained on the token you mentioned, then followed with some carefully labeled data from experts of different domains, different areas, those fine-tuning process in the Aurora GPT?
Yeah, well, that's a good question. So we are limited in some ways in that we don't have the vast budget of the companies that created these other models to engage underpaid people in third world countries to do things. So we're looking very closely at to what extent we can use other large language models to provide some amount of quasi-expert input, looking at ways of using other forms of computation for that purpose, and then hopefully a much smaller amount of truly expert input.
Thank you. So I guess maybe there could be volunteering efforts, so that's we can like volunteer to contribute.
That would be wonderful, yeah, I think very much so, yeah.
Hi, Professor. The companies that have built the larger models so far, are they supporting this effort? And this being a government project, any risk that they lobby to shut it down?
Well, we've certainly had some wonderful conversations with some of those companies who are really, I think, intrigued. The fact that they're interested in science and they're doing some excellent work, but that's not their primary focus. So I think they expect to learn from what we're doing. There are some of these, not companies, but non-profits like the Allen Institute that we're working very closely with. I don't think that that these companies would see this as a risk to them, given the lab's mission, the resources we have. I think they see us as being someone who will produce perhaps some interesting data, certainly interesting results, and perhaps an interesting source of people that they can recruit for their nefarious ends.
Any other questions?
Yeah, sure. There it is. Yeah.
I have a question. When you start training with a greater amount of modalities that are kind of, science is filled with tons of different modalities, do you envision any unique challenges? For example, that you'll have to change the manner of computing, change architectures, change anything else?
Yeah, no, I think that extracting information from is going to be really full of fascinating problems in dealing with mathematics. We're not at the point yet where we've identified any showstoppers, but there are certainly open questions that we haven't thought about how to answer.
Hi, Ian. Nice to talk. A lot of high-quality data often sits behind paywalls. Can you say what's going on regarding pulling that data out of Elsevier and other publishers?
Wonderful question. Yes, so we've got access to a very good collection of open data from the Allen Institute. We're talking to various publishers. We've got, for example, the ACM publications licensed to us, and it remains to be seen what will happen with, say, the likes of Elsevier. We know that they have made some of their articles available to other entities like Digital Science, so that there's at least some encouraging signs that we can get access to it as well. One thing that I think we're all interested in that regard is how does the quality of the answers we get out of the model, the scale with the variety and number of scientific articles that one has, and that's something that the Allen Institute and us are looking at. That will determine, how important it is that we get access to these additional articles.
All right. I think that's enough questions for now, so let's thank Dr. Foster one more time.
Thanks.